Welcome back to Larry's Classroom. We will continue our discussion related to powers of 10 and multiplying and dividing powers of 10. We'll start with another example. Ten to the negative first times 10 to the negative second times 10 to the third over 10 to the negative fifth. We work from left to right. We want to do the multiplication, then we're going to have another multiplication from here to the numerator of this fraction, and a denominator from the numerator, or division from the numerator to the denominator. We're going to do this multiplication first, and we're going to remember the rule, negative exponents. We add the absolute values of the exponent and use the negative sign. So this part here becomes, I'm going to do a little, like that. That's 10 to the negative 1 plus 2. Now, we can go ahead and convert this to a multiplication problem like we talked about before. We won't actually do the multiplication or division, but we'll go ahead and convert it. So this becomes 10 to the third. This thing here becomes 10 to the third times, and when we raise this 10 to the negative fifth into the numerator, it becomes 10 to the fifth times 10 to the fifth. So we've converted that. We actually haven't done the multiplication yet, and here we really haven't done the multiplication either. Multiplication won't be done until we add the 1 and the 2. But let's go ahead and do that. 10, 1 plus 2 is 3 to the negative 3. We did the conversion, 10 to the third times 10 to the fifth. Now let's do this piece. We have a negative sign, the positive sign. We subtract the two numbers, use the sign of the largest, so that becomes 10 to the, we got a positive 3 is larger than negative 3, so it's going to be positive, but we end up with 3 minus 3. And we'll just bring this guy down, times 10 to the fifth. We'll do this calculation here, 10 to the 3 minus 3 is 10 to the 0, which is equal to 1, right? Remember, 10 to the 0 equals 1. So we're just going to call this 1 times 10 to the fifth. So there's our answer, 10 to the fifth. 1 times 10 to the fifth is 10 to the fifth. So 10 to the fifth, this expression up here was equal to 10 to the fifth. Now we'll talk about numbers times powers of 10. So we're going to express some numbers. If we have, get rid of this too, 36 million. That's equal to 36 times 1 million, right? 36 million is 36 times 1 million. If we express this as power of 10, it becomes 36 times 10 to the 6th. And you probably remember that 10 to the 6th is equal to 1 million. That's a 1 and 6 zeros. 1 million is a 1 and 6 zeros. And if we have a small number, 0.0057, that's a pretty small number, 57 10,000ths. We can express that as 5.7 times 0.001. That would move the decimal place 3 places, which gives back to this right here. From 5.7, 1, 2, 3. But this 0.001 can be expressed as 10 to the negative third. So we can rewrite this as 5.7 times 10 to the negative third. And what we've shown here is that using powers of 10 gives us a compact way of writing very large numbers or very small numbers. Now if we want to multiply or divide numbers times the powers of 10, we will multiply and divide the number. To get the number part of the equation, we'll apply the rules for multiplication or dividing powers of 10 to get the power of 10 part of the answer. So we're going to give an example here. We're going to do a multiplication. 3 times 10 to the second, which we're going to multiply times 5 times 10 to the fourth. And we basically just said that we would multiply the numerical portion, the 3 times the 5, and then we use the rules for multiplying powers of 10 to multiply the 10 to the second times the 10 to the fourth. And that will give us, well, 3 times 5. Let's put that in parentheses. 3 times 5. That takes care of the numerical part. And the 10 to the second times 10 to the fourth will be, well, we'll write it. We'll go ahead and put it into parentheses first. 10 to the second times 10 to the fourth. And of course there's still implied multiplication here, implied multiplication here. We put two expressions in parentheses together. We're going to go ahead and do this part. 3 times 5 is 15. And we're going to do the part in parentheses using the rules for multiplying of powers of 10. Well, we have positive exponents. That becomes 10 raised to the sum of the positive exponents, 2 plus 4. When we multiply powers of 10, if the exponents are positive, we just add the exponents. That gives us the result. We'll do the adding of the exponents. We have 15 times 10 to the sixth. So we've taken these two powers of 10s, we've multiplied the numerical portion, we've put the powers of 10 together in parentheses. Here we actually did the multiplication of the numerical portion. Now here we laid out how we're going to do the multiplication of the powers by adding the exponents. They're both positive. Then we actually did the addition, so here we had 15 times 10 to the sixth. And using powers of 10 is a nice way to work with especially large numbers. Now we're going to do an example where we divide. This times 10 to the negative fourth over 3 times 10 to the negative second. Remember, we just said that if we're going to multiply or divide powers of 10s, we're going to multiply or divide the numerical portion. Then we will use the rules for multiplying and dividing powers of 10 to get the power of 10 portion. Well, 6 times 3, we'll just write that as 6 times 3, or 6 over 3, 6 divided by 3, excuse me. And we're going to multiply that, well, we just separate it first. 10 to the negative 4 over 10 to the negative 2. Now you remember, here we could just do this division, right? 6 times 3, or 6 divided by 3 would give us 2. To do this division, remember with the powers of 10, we convert it to a multiplication problem. We do that by moving the 10 to the negative 2 to the numerator, then it becomes 10 to the positive 2. So we're gonna go ahead and do this part. 6 times 3 becomes 2. And we're going to rewrite this as a multiplication problem. So we've got 10 to the negative fourth. But instead of dividing by 10 to the negative 2, we're going to multiply by 10 to the positive 2. We just change the sign of the exponent when we change it from a division to a multiplication. Let's continue carrying on down. We've taken care of the numerical portion, 6 divided by 3, 6 divided by 3, 2. Now we're going to use the rules of powers of 10. It's going to be 10 to the, well, when we have different signs on our exponents, we use the sign of the largest one, and we subtract the smallest from the largest, 4 minus 2. And we work this out. The 2, we finished that several steps ago. 10 to the negative 4 minus 2. 4 minus 2 is 2, and we apply the negative side that's on the outside of the parentheses. So we end up with 2 times 10 to the negative 2, which we can express as a decimal in the form of, well, if you take the 2, we want to move the decimal place 2 places this way, 0.02. The 2 right here, we move the decimal place 2 places to the right because it's negative, which makes the number smaller. 0.02 is smaller than 2. So this expression here, this division of powers of 10, of numbers times power of 10, we did the number portion, we did the power of 10 portion separately, we got the result of the number portion, we got the result of the power of 10 portion, and then we converted the whole thing to a decimal. Okay, now we have a little more complicated one. Well, right up here we got 2 times 10 to the negative 8th times 6 times 10 to the 5th, and that's all over 6 times 10 to the 13th, or 6 times 10 to the 3rd, negative 3rd. We have a multiplication and division. We're going to take care of the multiplication first. It's on the numerator portion of the fraction. We'll do the numerical part, and we'll also do the power of 10 part. So we're going to group them. 2 times 6. Remember, this parentheses being pushed together like that, there's implied parentheses. I could put little times there, or I could put a dot there. Or we could just leave it empty, and you would know that standard means multiply. So here we've grouped the 2 and the 6 out here. I'm going to go ahead and put the times, the multiplication symbol here. We're going to take care of the power of 10 part. Well, that's 10 to the minus 8th times 10 to the 5th. Then we'll go ahead and carry forward the denominator of the fraction. So let's go ahead and work our way over this way. We've got 2 times 6, that will become 2 times 6, 12. And now that's going to be multiplied by what's in here. Well, remember the rule? Use the sign of the largest, the one with the largest magnitude. So we're going to be a negative sign, so it's going to be 10. Put parentheses, and then we're going to subtract these and find the difference. 8 minus 5 goes in the parentheses. So we kept the same base, the 10. We've used the sign of the exponent with the largest magnitude, which we put right there. We put the actual subtraction into the parentheses. We haven't done anything with the denominator yet, so we'll carry that forward here. Now let's go ahead and come down here, 12. Put a fraction bar here. So how are we going to handle this? 10 to the negative 8 minus 5. 8 minus 5 is 3, so that becomes 10 to the negative 3. We still haven't done anything with this. 6 times 10 to the negative 3. We're going to move over here to the right and separate these so the numerical parts are separate, like we might do, like we've been doing. 12 over 6 times. Now, let's look at this piece. 10 to the minus 3 over 10 to the negative 3. You can kind of see that that's the same number in the numerator and the denominator. So that would certainly be 1. So we could just do the 12 by 6, 12 divided by 6, say it's 2, and call this 1. The answer is going to be 2, right? But we're going to move forward a little bit more with this. We're going to go ahead and do the division of 12 divided by 6, which is 2. And then we're going to rephrase this as a multiplication problem. So we're going to put in parentheses here, we're 10 to the negative 3 times, we'll make this a multiplication problem, that sign changed, times 10 to the positive 3. Well, we don't need the positive sign, just 3. It's no longer a fraction now because we did the division here and we converted this into it's no longer expressed as a fraction. We converted this division or this fraction into a multiplication. So let's move forward using the rules of multiplication of powers of 10. The 2 doesn't change, we've already handled that. And it's going to be 10 to the, we use the sign of the largest, which is positive. We subtract the largest from the smallest, which gives us 2 times 10 to the 0, which basically is 2 times 1, which equals 2. Now right here, you kind of see by the way I separated these out why 10 to the 0 is equal to 1, because when we converted this fraction with the same power of 10 in the numerators and the denominator to a multiplication, we found that the exponents canceled and left an exponent of 0. So it's pretty apparent, I think, that this number was 1. The numerator and denominator is the same, and that's always going to be a 1. We did this, we did the actual using the rules of dividing powers of 10, and we worked out to a 10 to the 0. So we saw that this and 10 to the 0 were the same number. And it's pretty easy to see that was 1. And we had also stated as a fact before that 10 to the 0 is going to be 1. And you're going to see any time you have the same exponent in the numerator as in the denominator for a power of 10, that the answer is going to be 1. That the value is going to be 1. You probably remember, I think it was in the last lesson that we told you that 10 to the 0 was equal to 1. I'm hoping that that'll give you a little bit better idea why that is true. Now, if we add or subtract numbers times powers of 10, times powers of 10 of 10, the power of 10 must be the same for both. power of 10 must be the same. So if we're going to subtract two numbers that are multiplied times powers of 10, we need the same exponent, or the same power of 10 in both of them before we do the addition. We do an example of a simple one, which is already in the same 4 times 10 to the 5th plus 3 times 10 to the 5th Now these are both in the same power of 10. They're 10 to the 5th. So the rule for adding these is add the numerical portion and leave the power of 10 alone. So we have 4 plus 3 times 10 to the 5th. We didn't change anything on the power of 10, but we do add the numerical portion. Well, 4 times 3 is 7 times 10 to the 5th. The 10 to the 5th didn't change. We're adding up 10 to the 5ths, I guess is a good way to look at it. Now, if these do not match, we have to modify the number so they do have the same power of 10 before we do the addition or subtraction. So we're going to do a couple examples of how to do that. We're going to give an example of a number. 35 times 10 to the 3rd. Let's say we needed to change that into 10 to the 4th. How would we do that? Well, if we're increasing the exponent, we need to move the decimal point on the numerical portion to the left. What we're doing here is making this number larger and this number smaller. If we move the decimal place 1 to the left, that's like dividing by 10. If we increase this by 1, that's like multiplying by 10, and it balances out. So we still have the same number. So let's convert this so that it isn't. So instead of 10 to the 3rd, it's 10 times 10 to the 4th. Well, we're going to have to increase that, so we want to decrease this. We move to the left, 3.5. We decrease that, move to the left. We increase this times 10 to the 4th. So we basically multiplied that number by 10. 10 to the 3rd times 10 is 10 to the 4th. We divided this number by 10. 35 divided by 10 is 3.5. So basically, when you're going left with the decimal place, you're increasing the power. If you're going right with the decimal place, making your numerical portion bigger, you're decreasing the power. We'll do another example, very much like the one we just did. 613 times 10 to the -4th. Now, we want to make this, instead of 10 to the -4th, we want a power of 10 to the -2nd. Let's write that over here. 10 to the -2nd. Now, what did we do? -2 is larger than -4. If you look about the number line, 0 here, plus in this direction, negative in this direction. We'd have -2 somewhere here, -4 somewhere here. So -2 is a larger number than -4. So we increased the value of this. We made that number bigger. So we need to make this number smaller. We made this number bigger by 2. So we need to make this number smaller by moving the decimal place to the left 2 places. Well, if we had 613, we move the decimal place to the left, we end up with 6.13. So we kept a balance by making this smaller and that larger. We kept a balance. Same thing here. We made this smaller and that larger. Now we're going to do another example. And this is going to be one where we're going to make the the power smaller, which we'll be doing a little bit differently. 2.74 times 10 to the 5th. We're going to want to make this smaller, which means we're going to have to make that larger. When we make this smaller, we move our decimal place to the right to maintain our balance between decimal places and powers. And we're looking to make this one to be 10 to the 3rd. So we want this 10 to the 5th to become 10 to the 3rd. So we made 5 too smaller to get the 3. We reduced 5 by 2. So we need to move the decimal place 2 places to the right to make this number larger to make up the fact we made this number smaller. Well, 2.74, 2 places to the right becomes 274. We've kept our balance, as you can see. We're going to do one more example of this type. We're moving to the left, we're making this larger, we're making the exponent or the power smaller. We're moving to the right, we're making this larger. We're making our exponent or power smaller. We're moving to the left, we're making this number smaller, we're making our exponent or our power larger. Move to the right, made this number larger, we made the exponent smaller. So we're going to one more example. 1.42 times 10 to the negative 3rd. So we're going to want to make this smaller, which means we've got to make this bigger. We're going to make this smaller by one number. So we move this decimal place one number to the right to make it bigger. We're looking to get to 10 to the minus 3rd or minus 4th. So we're going to put that over here. And this is what you'll have to do if you're going to add or subtract powers of 10. You look at where you want to go, and that will tell you what to do with this. We wanted to go to negative 4. We made the exponent one smaller, so we got to make this, move the decimal place to the right to make it 10 times larger. This made this number 10 times smaller by making the exponent one less. And we want to move our decimal place to the right to make the numerical portion 10 times larger. Keep our balance, keep the number being the same value. 14.2 times 10 to the minus 4th is the same as 1.42 times 10 to the minus 3rd. We made this number one smaller. We moved the decimal place 1 point to the right to make this larger. We made the exponent one smaller, which made the number 1/10 as much. We moved the decimal place 1 point to the right, which made this number 10 times larger. So we made this number 1/10 as much, we made this number 10 times larger. That keeps our balance so it still has the same numerical meaning, same value, just written in a slightly different form. And if you want to add or subtract powers of 10, you got to make the powers the same. So you make a choice, which way do I want to make it to match them up, and then you add the numerical portion. And at that point, once you've made the powers of 10 to be the same, you don't have to change them. They stay good. Now, if we want to change to an ordinary number, we've got a power of 10 number. We're going to change it to an ordinary number. 0.943 times 10 to the 5th. By ordinary number, I mean with no power of 10. Well, we look at the exponent part of our power of 10, the power, which is 5, which basically means we're essentially reducing that to 0. So we got to move this thing 5 to the right. So we just write 943. We've moved it 2 places to the right, but we need 2 more. 94,300. We made this 0, which means we got rid of it because it's times 1, and then we move this 5 places to keep the value the same. We're going to do a few more examples of this. 7.9 times 10 to the third. Again, we want to make this an ordinary number with no power of 10, which means we want to reduce this to 0, this exponent to 0, which makes this equal to a 1, but we've basically reduced this power by 3. We need to move the decimal place 3 to the left to make it 1,000 times as large, meaning this is 1,000 times as small. So 79 moves at once. We got to go 3 times, 3 points. So there we go, 79,000 or 7,900. So 7.9 times 10 to the third is equal to 7,900. 7.9 times 10 to the third is equal to 7,900. We got rid of this. We moved the decimal places 3 to the right. Now we're going to have some that we go the other direction. And you might have, maybe when you're all done doing your power of 10, you want the answer expressed this way. And by the same token, you want to express as a power of 10, 1, 2, 3, 4, 5, you know, how many decimal points you want to put on there gives your exponent. So 24.3 times 10 to the negative 3. Now we want to get rid of the exponent here. Well, negative 3 up to 0 is making that larger, so we got to make this guy smaller. And that means move our decimal place 2 or 3 places to the left. So if we had the 24.3, 1, 2, we got to add a 0. You see 0.0243 is what would happen if you move the decimal place 2 points to the left. We made the number larger, we made the multiplier bigger. One more and we'll move on to the next step here. 332 times 10 to the negative 5. We want to express this as a regular number without a power of 10. We're going to be making this thing 5, go from 5 to 0, so we're going to move the decimal place 5 to the left. Because we made this number, oh, this is a negative 5. That's why I don't look right. Yeah, negative 5. So when we go to 0, we're making this number larger. 1 is bigger than 10 to the minus 5th. So we're going to be making this number smaller. When we get rid of these negative numbers, we need to move our decimal place to the left. We're getting rid of positive numbers, we move our decimal place to the right. We're trying to continue to keep everything in balance. So we got the same number. So I'm going to write the 332 over here. 1, 2, 3, 4, 5. So that's what happens if we move the decimal place We got rid of the negative 5, we moved our decimal place 5 to the left. We got rid of the positive 3, we moved our decimal place 5 to the right. We got rid of the positive 5, we moved our decimal place 5 to the right. We got rid of the negative 3, we moved our decimal place 5 to the left. This keeps everything in balance, the numbers still have the same meaning. And we're not lying when we put the equal sign in there. Okay, we're going to add these numbers up and we're going to express the answer as powers of 10 and in ordinary notation. So we got this number here, 7 times 10 to the 4th plus 6 times 10 to the 3rd. So we have a choice. We have different powers of 10. We can change this one to a 3 or change that one to a 4. Let's go ahead and change this to a 3. We're making that smaller, so we got to make this larger. So instead of 7 times 10 to the fourth, we have 70 times 10 to the third. You see how we made that number smaller, so we moved our decimal place to the right, which made that number larger, kept things in balance. Plus 6 times 10 to the third. Now we have two numbers we can add together that are in the same power of 10, so we can add the numerical portions, 70 plus 6, and we don't do anything with the, when you're adding, once you got them in the same power of 10, we don't do anything with the power of 10, we keep it as is, times 10 to the third. So we're going to go over here, 70 plus 6, 76 times 10 to the third. There it is as a power of 10. We've done the summation, the addition, but we also want to express this as an ordinary number. Well, 76 times 10 to the third, we get rid of this 10 to the third, that means we've got to add 3 decimal places right. We made the 3 a 0, we made this smaller, we've got to go 3 decimal places to the right to make this bigger. So that becomes 7600. Or 7, I don't know, I gotta go one more than that. I just 76,000, because my decimal place was right here. Now, we're going to do this, if we'd taken this problem and we went the other way, we're going to leave the 7 times 10 to the fourth unchanged. So that means we got to make this one be 10 to the fourth. Well, 10 to the fourth, we increase that number, which means we got to make this number smaller, so we got to move the decimal place to the left. We make this one larger, we want to make that one smaller, 0.6. You increase this by 1, we move this decimal place 1 to the left. Now we have the same powers of 10. So we can add the numerical portions, 7 plus 0.6, and we're not going to do anything with the powers of 10 because we've got them in the same power of 10, the same exponent, times 10 to the fourth. Now what's 7 plus 0.6? That's 7.6, right? We're still times 10 to the fourth. So we've got the number in power of 10. Notice these look different, but if we made this a 3, we'd make that to the left. It'd be 76 times 10 to the third. But now we want to convert it to an ordinary number. Well, we got the 7.6. We want to move the decimal place forward to the right to get rid of this. Well, if we write 76, we've moved it 1 to the right. We've got to go 3 more, so we've got to add 3 zeros. So there you are. We got the same answer regardless of which one we changed to match. In this one, we changed the 10 to the fourth to match the 10 to the third. We added it all up. We got a 76 times 10 to the third. We expressed that as an ordinary number. Got 76,000. When we did the problem the second time, we left the 10 to the fourth the same. We changed the 6 times 10 to the third to the 6.6 times 10 to the fourth. We added the numerical portions. The power of 10 was already handled. We got them in the same power of 10. Here we added the numerical portions. Here we converted this power of 10 to an ordinary number. And we got to the same number both times, which is always a good thing when you take two different methods in mathematics. You always want to hope you get to the same number, because if you don't get to the same solution, something must not have been done correctly. We're going to do one very similar. We're going to do it 2 different ways. Actually, we're going to do it 3 different ways. 3 times 10 to the negative 2 minus, now we're doing subtraction, 4 times 10 to the negative third. Well, subtraction and addition, pretty much the same rules. Got to be in the same powers of 10. In this case, we'll be subtracting the numerical part once we get them in the same powers of 10. Let's make this one to be -3. So it's going to be 10 to the -3, which we made this number smaller. We're going to make this number bigger. So that becomes, instead of 3, we move it 1 to the right. We get 30 times 10 to the -3. This one we don't do anything with because we've got them in the same value. So now we're going to subtract the numerical parts. 30 minus 4. And we've already got the power of 10, the same power, so it's still going to be times 10 to the -3rd. 30 minus 4 is 26 times 10 to the -3rd. And now we're going to express this as an ordinary number, which is going to be a decimal. We get rid of this. We made that bigger. We got to make this smaller. We got to move the decimal place 3, making this larger. We're getting rid of the -3. Basically, we had to move the decimal place 3 to the left. So it becomes 0.026, 1, 2, 3 from where it originally was. We're going to do the same problem. This time we're going to convert the other. Instead of converting the 10 to the -2, we're going to convert the 10 to the -3. So we're going to, this is unchanged. 3 times 10 to the -2. Still going to subtract, but the 4 times 10 to the -3, we want to make this be -2. So put that in here, times 10 to the -2. We made this larger, so we got to make this smaller, which means we went from -3 to -2. That's getting larger. We got to go 4 to 0.4. Keep things balanced. We moved this to the left when we made that larger. We moved this to the right when we made this smaller. So now let's do now we have 3 minus 0.4, and we've taken care of the powers of 10, so it's times 10 to the -2. 3 minus 0.4, that's 2.6, times 10 to the -2. And when we drop this, we got to move the decimal place 2 to the left, so that becomes 0.026. Same answer we had before, right? Now we're going to do it one more way. We're going to convert both of these to decimals first and then do the subtraction. Well, 3 times 10 to the -2. Get rid of this. We want to move the decimal place 2 to the left. So that becomes 0.03. So we're going to do subtraction. This one we want to express as a decimal. We get rid of the -3. We need to move this thing 3 to the left. Minus 0.004. So that's the decimal equivalent of that. The decimal equivalent of that. We do the subtraction. Let's line them up like this. 0.03. We're going to add a 0 just to allow our subtraction. It doesn't change our precision, but we added that so we can do our subtraction manually. We could do the calculator if you wanted to, but we're going to change that to 2, borrow the 1. 10 minus 4 is 6. 2 minus 0 is 2. 0 minus 0 is 0. So you can see that we got the same answer with every method. 0.26, 0.26, 0.26. It didn't matter if we changed the -3, the -2 to a -3 to match that -3, or if we changed the -3 to a -2 to match that -2, or if we converted them to just decimal fractions to start with. We got the same result in every case. Now this course is called mathematics for electricity and electronics. So we're going to do a little electrical example using the powers of 10. Got a little circuit here. We got a voltage supply. This is a symbol for a resistor. I'm just going to put an R here. And I'm going to go I. We would have some current flow. If we had a voltage source connected to a resistor, we would have some electrical current flow through that resistor. And Ohm's law says that voltage equals current I times resistance. We want to find the voltage in the case that I equals 3.6 times 10 to the negative third amps, and that resistance equals 1.5 times 10 to the third ohms. Voltage we measure in volts, current I we measure in amps, and the I is a symbol for intensity, by the way. R, resistance, we measure in ohms, and we use this little Greek letter omega as a symbol for ohms. So let's work this out. We got V equals I of 3.6 times 10 to the negative third, and that's multiplied times 1.5 times 10 to the third. So remember, we multiply the numerical part, 3.6 times 10 to the, just do the numerical part, 3.6 times 1.5, and we're gonna multiply the powers of 10 part, 10 to the minus 3 times 10 to the positive 3. Well, 3.6 times 1.5 comes to 5.4. And I think by now we'll put the times in there. You can see that we will use the sign of the largest, which is going to be positive, and we'll subtract the largest from the smallest from the largest. Well, 3 minus 3 is 0. That's 10 to the 0, which is equal to 1. So our answer is 5.4 volts. We solved a simple little electric circuit. We utilized our powers of 10 arithmetic. All right, we're going to do one more example here. Given that Ohm's law equals I equals V over R, I current in amps, V voltage in volts, R resistance in ohms. If we have a voltage equal to 9.6 volts and a resistance equal to 1.5 times 10 to the third ohms, let's find the current. Well, we're going to start by taking this formula and we're going to substitute some values. We're going to say that I will equal to 9.6 volts divided by 1.5 times 10 to the third ohms. And we're working on powers of 10 and such, so we're gonna separate this to find our calculations more simply done. So we're going to rewrite this first of all. 9.6 times 10 to the 0. Remember, 10 to the 0 is equal to 1. Anything to the 0 power is equal to 1, and that's going to be volts over 1.5 times 10 to the third ohms. So we're going to do our calculations here. I'm going to move this volts over ohms over here, which you see equals amps, so we're going to end up with units in amps. So this will basically be amps when we're done. We took the volts over ohms and replace it with current, which is we would do in amps. We're going to rewrite this a little bit. 9.6 over 1.5. That takes care of the numerical portion times, I don't want these parentheses here just yet, 1.6 times 10 to the 0 over 10 to the third. There's a couple ways we could do this. I'm going to do it this way. The numerical portion will give us a numerical part of our answer, 1.5. I'm going to put that in parentheses now. And that's going to be times 10 to the 0. And we're going to convert this division to a multiplication. So this will be times 10 to the negative 3. Carry this guy down here. 9.6 over 1.5. And now we're going to use our rules for multiplying exponents. Remember, we take the larger magnitude one, we subtract the smaller magnitude exponent, we use the sign of the larger magnitude one. So this is times 10. We're going to use the negative sign here, and we're going to do the 3 minus 0. And then I'm going to go ahead and leave the amps on here, the units, because it's going to be in amps. Now if we do the arithmetic on the 9.6 divided by 1.5, we come up with 6.4. And now we do the arithmetic here. The 3 minus 0 is 3, use the negative sign, times 10 to the negative third, and that's still in amps. So that, we've used this simple little circuit, series circuit, it's a voltage source and a resistor. This was the symbol for the resistor. We've used Ohm's law, which is the relationship between voltage, current, and resistance in an electric circuit, the mathematical relationship. We were given some values of voltage, 9.6 volts, and resistance of 1.5 times 10 to the minus third ohms. We put those into the formula. Then we rewrote these both as powers of 10. Then we separated the numerical part from the powers of 10. Then we converted the division of the powers of 10 to a multiplication. Then we actually did the calculation of the numerical portion, and we did the calculation of how we multiply powers of 10. So we have 6.4 times 10 to the minus third, which can also be expressed, this is a negative 3 for exponents, so that can be 0. We got to move the decimal place. Well, let's write this down here a little bit. Let's write our 6.4. And this is negative 3, which means move the decimal place 3 places to the left. 1, 2, 3. We add a leading 0. We'll get rid of this guy. So we end up with 0.0064 amps in the decimal version, and 6.4 times 10 to the minus third amps in the power of 10 version. So we've done a little electrical example of math and powers of 10, and we've seen again, which I guess we've just seen, the one version of Ohm's law, where if we have the voltage and resistance supplied, we can calculate the current. And by the way, I is current in amps. When this is volts and this is ohms, I will be current in amps, but we use an I for intensity, for the intensity of current, the amount of charge carriers flowing, the amount of electrons in a given time. V was voltage in volts, R was resistance in ohms, I was current in amps. Anyway, thanks for coming in. Hope you enjoyed today's lesson, and be sure to like and subscribe. And until the next time, be sure to keep on learning.